Okay, so you know how sometimes when you're really digging into interview prep for those like senior software engineer roles, you start seeing certain themes pop up over and over
Oh,
again.
yeah, definitely.
And like one of the big ones is how the systems we build deal with change and specifically changes to their data.
Makes sense. That comes up a lot.
So we figured let's do a deep dive into this whole area of data encoding and schema evolution.
Yeah, let's break it down.
Why it's so important, what different approaches are out there, and
Hmm.
yeah, just really try to like demystify it for everyone out there going through the interview grind or, even for folks who are already senior engineers and just want to like brush up on these core concepts.
Totally. I mean, you can design the most elegant system in the world,
Hmm.
but if it can't handle change gracefully, it's eventually going to become a bottleneck or worse.
Right, exactly. You got to think about the long game and those real world scenarios where things are constantly in flux.
Like new features, shifting user needs, the whole business landscape can change, and your systems need to be able to adapt without breaking.
Yeah, and that's really what evolvability is all about, right?
Yeah, evolvability, that's the name of the game.
It's about building systems that are flexible, resilient, and can like roll with the punches.
Exactly. You don't want to be stuck with a system that crumbles the moment you need to make a tweak.
And a big part of that flexibility lies in how you handle data because let's face it, when a new feature comes along, you're almost always going to need to store new types of information or, maybe reshape how you use what you already have.
Right, the application changes and the data model needs to keep up.
So let's talk about how different types of databases handle these shifts. Like on one hand, you have relational databases, right? They're like the classic, well-structured approach with a well-defined schema, almost like a blueprint for your data.
Yep, everyone has to stick to the blueprint at any given time.
And if you need to tweak that blueprint, you usually have to perform a schema migration. It's kind of like renovating your house. You have to temporarily disrupt things to
Hmm.
change the underlying structure.
I like that analogy. It really captures the essence of schema migrations in relational databases.
And then you have the other side of the coin, like the schema on read or schemaless databases. These guys offer more flexibility because they don't enforce a rigid schema when you're writing data.
It's like saying you can build your house however you want as long as it stands up.
So you can have different shapes of data coexisting, potentially written at different times by different versions of your application.
Yeah, it's all about accommodating change as it happens.
You gain agility, but you also push some complexity into your application code, which is a trade-off to think about when you're choosing a database.
Definitely need to weigh the pros and cons carefully.
Okay, so we've got these data format changes happening, and at the same time, your application code needs to be updated to understand and work with these new formats. But deploying new code across a large system isn't always like flipping a switch. Things get messy in the real world.
Yeah, especially in distributed systems, you can't just instantly update everything everywhere.
Right. And this is where things get really interesting because we need to consider what happens when you have different versions of your code and different versions of your data existing at the same time. It's like a time work situation.
It's like having different generations of your family living under the same roof.
So imagine you've got a server-side application undergoing a rolling upgrade. You might deploy the new version of the code to a fraction of your servers initially, and then gradually expand it until all servers are running the latest version. This helps minimize service interruptions, which is, super important for a lot of applications.
That's the standard approach for zero downtime deployments.
But it means for a while, you've got old and new code running side by side, potentially interacting with the same data. It's like a juggling act.
You need to make sure they don't step on each other's toes.
And then think about client-side applications like mobile apps. Users don't all update to the newest version the second it's released, right?
Some people hold on to those older versions for dear life.
Exactly. So you might have folks running versions of your app that were built months or even years ago, and they're still interacting with your backend system, which might have gone through multiple data format changes in the meantime.
Yeah, it's a recipe for chaos if you're not careful.
And this is where the concept of compatibility becomes absolutely essential. You got to make sure that these different versions can play nice together.
Compatibility is the glue that holds everything together.
So let's break down the two key types of compatibility, backward and forward compatibility, starting with backward compatibility.
Backward compatibility is like making sure your new phone charger still works with your old phone.
Exactly. It's about making sure your newer code can still read and correctly interpret data that was written by an older version of the code. It's like being able to read the past of your data.
And this is usually the easier one to achieve because the developers of the newer code, They know the previous data format they can build in logic to handle it, maybe by providing default values for new fields that didn't exist in the older data, or by transforming the old data into a format the new code understands.
Right. It's about making sure the new kid on the block can still understand the language of the old timers.
And then you have forward compatibility, which is kind of the trickier one. This
Yeah.
is like designing your phone charger today so that it'll still work with phones that haven't even been invented yet.
Yeah, that's a great analogy because with forward compatibility, you're trying to make sure that an older version of your code can still somehow read and not completely freak out when it encounters data written by a newer version, which might contain new fields or structures the older code wasn't designed to handle. It's like preparing for the future of your data.
It's all about anticipating the unknown.
And this often involves the older code being designed to gracefully ignore information. It doesn't understand, like maybe the data format includes indicators about which fields are present, and the older code can just skip over the extra fields it doesn't recognize.
It's like teaching your dog to ignore girls. You can't always predict what they'll encounter, but you can train them to handle it.
Okay, so we've got this data flowing through our systems, whether it's sitting in a database or being transmitted across a network. How does it actually get from those in-memory structures we use in our code, like objects and lists and dictionaries, into a sequence of bytes that can be stored or sent? This is where data encoding steps in.
It's like translating between different languages. You need a way to convert the information from one format to another.
Think about it like this. Inside our applications, data is organized in ways that make sense for the CPU, often using pointers to connect different pieces of information. But when you need to save that data or send it over a network, those memory addresses become meaningless.
It's like trying to use a map of your neighborhood to navigate a different city. It just won't work.
You need a self-contained linear sequence of bytes, something that can be written to disk or sent over the wire without losing its meaning. And that's what encoding does.
Encoding serialization or marshalling. It's all about transforming those in-memory data structures into a portable format.
And then you have the reverse process, decoding or deserialization or unmarshalling, which takes that byte stream and reconstructs the in-memory data. It's like unpacking a suitcase after a trip.
You're putting all the pieces back where they belong.
And this whole back and forth translation, it's crucial for persistence and communication. It's the foundation of how our systems store and share data.
And what's really interesting is that different encoding formats have different ways of dealing with schema evolution and compatibility. Some formats are very rigid and tightly coupled to a specific schema, making evolution more challenging, while others are designed with flexibility in mind, allowing for changes to the data structure without breaking things.
Exactly. Like some formats are more like those old, delicate antiques that you're afraid to touch, while others are built to be more like Lego blocks. You can rearrange them and build something new without breaking the old structure.
And there's a whole spectrum of formats out there, each with its own strengths and weaknesses. We're talking about formats like JSON XML protocol, buffers, Avro thrift, you name it. Each one has trade-offs regarding readability, efficiency, and how well they manage schema evolution.
It's like choosing the right tool for the job. Sometimes you need a hammer, sometimes you need a screwdriver.
And understanding these trade-offs, that's a key part of designing robust, evolvable systems. And it's something that interviewers love to dig into, especially for senior roles.
They want to see if you've thought about these things in the real world.
Because these aren't just theoretical concepts, they have real practical implications.
So let's do a quick recap. We've talked about how change is inevitable in software and how that directly impacts our data. We've looked at different ways databases handle those changes. We've explored the complexities of having different versions of code and data coexisting, and we've emphasized the importance of both backward and forward compatibility.
It's all connected.
And finally, we touched on how data encoding acts as that bridge between our in-memory data and the byte streams we use for storage and communication.
It's the glue that holds it all together.
So for those of you out there gearing up for senior software engineer interviews, remember that being able to clearly explain these concepts, it shows that you understand the realities of building and maintaining complex systems, that you're not just thinking about writing code in isolation, but you're also considering the long-term adaptability and health of the software you're building.
Shows you're thinking like a senior engineer.
Which leads us to our final thought to chew on as you continue your interview prep. Take some time to think about specific real-world scenarios where backward and forward compatibility become really tricky.
Like, what are those edge cases that keep you up at night?
What design patterns or strategies have you encountered or can you come up with that can help address these challenges in real systems? Think about things like adding a non-nullable field to a data model that was previously nullable, or drastically restructuring a core data entity. How do you make sure older versions of your application don't crash and burn when they encounter this new data? And how do you make sure newer versions can still handle the old data gracefully?
It's all about finding elegant solutions to messy, real-world problems.
And those are the kinds of problems that senior engineers are expected to solve.
It's a challenge, but it's also what makes this field so interesting.
It's like solving a puzzle, but the puzzle pieces keep changing shape.
You got to be adaptable, creative, and think ahead.
Exactly. Well, on that note, we encourage you to keep exploring these topics and to think about how these principles apply to the technologies and system designs you encounter in your work and your interview prep. Thanks for diving deep with us.
Keep learning, keep building, and good luck with those interviews.
See you next time.
Catch you later.